Hello, my name is Paul Craig, and I'm a professor of biochemistry at the Rochester Institute of Technology in Rochester, New York. I've been teaching at RIT for almost 25 years now, and I'd like to share some of my experiences of working with undergraduate research students. Perhaps you're an undergraduate student right now. Maybe you're just starting early in your career in college. And you look around and you have this image of the scientist as this solitary genius working in the lab by himself, thinking brilliant thoughts, and you think, I could never do that. Well, in fact, most science involves communication and working in teams. Or maybe you just took an organic chemistry exam and you got your grade back. And you're kind of in the middle of the pack. You're not the top grade winner in that course. And you think, well, maybe I'm just not cut out for this. Well, I'd like to encourage you to rethink that. In fact, the ability to take exams has no corollary once you get out of school. The real important skill is the ability to solve problems, to be persistent, to be passionate about what you're studying, to follow through on things. When I think of research, I think of my own experiences in graduate school. And when I was in graduate school, I took some difficult classes and I passed the exams and so forth, but the things that I remember are the things I actually did at the bench. At the bench, I learned to do experiments, I learned to design experiments, I learned to interpret the results I get. I also learned about failure because I failed a lot. And I learned how to look at those failures and try to find new approaches that would help me to overcome those situations or to understand better why the experiment went a different direction than I wanted it to go. Now you might ask, why should I do research? Because I don't think I'm going to end up in a career as a scientist. Well, the fact is that by doing research, you encounter some things that I mentioned, particularly failure and problem solving. In school, you've probably heard about the scientific method and how that's opened up the world to us. And the advances we've seen as a result of the scientific method and deductive reasoning have been extraordinarily powerful in expanding opportunities. One of the things they leave out, or two of the things they actually leave out of this, are failure and problem solving. And I will say that for every experiment I've designed in the lab that worked, I probably failed 10 times, and I had to find ways to solve the problems I encountered there. So if you engage in research, even as a non-scientist, you're going to encounter problems, you're going to encounter failure, you're going to learn how to overcome that failure, how to approach that failure. You're also going to learn to explain complicated issues in simple terms that are more accessible to your peers, to the general public. You're going to learn how to look at a big problem and break it into smaller parts. There are many advantages to doing research. And it's really great when you can move from a classroom setting to actually engage in what we call discovery-based research, where you're finding out new things all the time. In the research lab, there's a couple of different models that we use to train research students. One is called the Apprentice Model. This is a case where you're working one-on-one with your faculty advisor, and the faculty advisor teaches you the techniques. They teach you how to form a hypothesis, how to test that hypothesis, how to design an experiment, how to use techniques, how to collect data, how to interpret those data. This involves things like using graphs and tables and charts, using statistics. And once you've interpreted that data, you draw conclusions. Was your hypothesis confirmed or was it disproven? In which case, do you need to go to a new hypothesis? Where do you need to move from there? But this is mostly done in a one-on-one setting where an individual professor works with an individual student. And this is how I did my graduate work. And this is a pretty standard model for graduate education and for research training in general, not just for graduate training, but for research training in general. A second model I'd like to present is the CURE model. Now, CURE stands for Course-Based Undergraduate Research Experience. In a CURE model, students come into a lab course, and the lab course is like other lab courses in that they're there with a group of other students, usually 12, maybe 15 students along with a professor and maybe a teaching assistant. But the difference in this case is The students don't know the answer to the problem they're trying to solve. The professor and the TA do not know the answer either. And so everybody's moving in the same direction, trying to discover some new knowledge. And this really is discovery-based research in the teaching lab setting. I'm working with a group of about 14 faculty on 8 different campuses to design and to assess a cure-based approach to a biochemistry lab that includes both wet bench methods that are typical in all biochemistry labs, things like protein expression, chromatography, electrophoresis, and measurement of enzyme activity, along with some computer models or computer techniques for predicting the function of protein based on its sequence, based on its structure, based on what we call docking, where we try to bind small molecules to a protein structure. So the students combine those techniques. And early on, we've found some interesting results. We found that the students in that setting, some of them get frustrated, some of them get disengaged, but some of them engage. One of the ways they seem to engage most powerfully is when they have to communicate their results to other students and share their ideas with each other and then build a hypothesis from there on the next steps to take. So in that setting, we're very encouraged, but we're also in a very early exploration state. But in either the Apprentice Model or the Cure Model, students are engaged in research and they're discovering new things. So to sum up, I'd like to emphasize that research is an important skill to learn whether you're going to become a scientist or whether you're going to enter a different career, because you may need to communicate about science at home, at work, maybe in some specialized setting like in a jury box. No matter what the setting is, learning by doing research can be very powerful. My own personal experiences, I've had students in my research lab who've come in as first-year students. They've asked questions that I wouldn't have asked because I've been trained too long in this area. But their questions led us to new opportunities and changed the way we did research. In the process, I've had the opportunity to watch them grow as scientists. I've also had the opportunity to see my heart and my mind opened up to newer and better ideas to learn new things. I highly recommend research to students, and I also highly recommend it to faculty to engage with undergraduate students in their research labs. Thank you very much for your kind attention.